Greetings. I'm Deborah Lawrence with the Federal Aviation Administration and a member of the Institute of Navigation's Executive Committee. Welcome to today's webinar, Hurricane Hunters Navigating a Plane Through a Hurricane. With the hurricane season starting in just a matter of days, this is a timely topic and it provides an interesting application of positioning, navigation, and timing in the most challenging of environments. If you work in the field of positioning, navigation, and timing, there is no better profession nor organization for you to belong to than the Institute of Navigation. Membership in ION connects you with the top leaders in the field and the people who can and will influence your career the most. If you are not already a member, please go to ion.org and join today. I wanted to let you know that registration for the Institute of Navigation's ION GNSS 2021 meeting is open. This will be our first in-person meeting in more than a year, and we're looking forward to it. We're going to be meeting in September 2021, September 21st through the 24th, and it will be in St. Louis, Missouri. Here's a brief invitation for you to join us from our ION president, Frank Van Degelen.
Hello, I'm Frank Van Degelen. I'm president of the Institute of Navigation. We're excited to be meeting again in person this year at the ION GNSS Conference, St. Louis, Missouri in September. At ION GNSS, you'll meet the people shaping the future of GNSS. Attending this conference is the single most important thing you can do for your career this year. View the entire week's activities at ion.org/GNSS. I'm excited to be traveling again and I hope you are too. Please meet me in St. Louis at ION GNSS 2021. What do you think, Mookie? Is that okay?
Thanks, Frank. You noticed that there was a puppy in there. That's Frank's puppy, Mookie. On to the webinar. Today's webinar is being presented by Lieutenant Commander Brian Richards. Brian is the chief of the training section at NOAA's Aircraft Operations Center and the instructor navigator on NOAA WP3D Orion Hurricane Hunters. As the chief of the training section, he is responsible for the development, implementation, and tracking of the Aircraft Operations Center ground and flight training programs for 9 aircraft and over 100 employees. As a WP3D Orion navigator and an instructor, he is responsible for the safe navigational guidance, position reporting, long-range communications, and mission coordination for the WP3D aircraft, as well as the training, qualification, and certification of all current and incoming navigators across all of the mission sets for the WP3D. That's a lot of work. Lieutenant Commander Richards received his commission in the U.S. Navy and a Bachelor of Science in Ocean Engineering from the United States Naval Academy in May of 2009. Prior to transferring his commission to the NOAA Corps in 2017, he served 6 years in the Navy as a Naval Flight Officer with the Patrol Squadron 4 and as a Level 500 Weapons and Tactics Lead Instructor with Commander Patrol and Reconnaissance Wing 2. Brian, his wife, and 2 sons live in Lakeland, Florida. And in his off time, Brian enjoys woodworking, basketball, surfing, reading, and traveling. Please note that this webinar will be available for the viewing at a later time and on the ION website and at ION's YouTube channel. There will be a Q&A after Brian has finished his presentation. If you have questions, please submit them by clicking the Q&A icon at the bottom of your screen. I want to thank Brian for his time and for giving us the opportunity to learn a little bit more about how navigation technology is being used in difficult conditions. At this point, I will turn it over to Brian. Brian, take it away.
Well, good morning, everyone. Again, my name is Lieutenant Commander Brian Richards, and I'm a NOAA Corps officer and currently serve as an instructor navigator and the Chief of Training Section for NOAA's Aircraft Operations Center in Lakeland. Before I tell you a little bit more about myself, I want to thank the Institute of Navigation for having me today. I'm actually really excited to have found this community, totally related around position, navigation, and timing. I feel like I'm at home here. I spent most of my professional career in some way, shape, or form dealing with navigation. As I was doing my research and in the meetings with the ION leadership, I quickly realized how accomplished the members of the institution are and how knowledgeable about your given fields you may be. So I very quickly got nervous. I'm scared of a misstep or a misquote, with the limited amount of knowledge that I may have about the systems and things that I do. So I'm very humbled to note that, you are an accomplished group of people, and there may be something that I don't necessarily know about. So I'm more than happy to take questions, and any unanswered questions after the brief. I'll take those questions for action and get those answers hopefully back to the ION leadership. I'm quickly reminded of an old saying, and that's, if you think you're the smartest person in the room, then you're in the wrong room. So with this brief and with your community, I think it's safe to say that I have truly found the right room. So I'm humbled to be here again. I just want to express my gratitude and thanks to the Institute of Navigation for having me. I'd be remiss if I didn't take this opportunity to give a quick shout out to my alma mater, the U.S. Naval Academy, and say, go Navy, beat Army. We're behind you guys. And I won't apologize if there are any Army fans in the audience. Now I'm going to go over a couple of notes for rules of engagement for the talk. I'm going to talk for about 30 to 40 minutes. I'll have a moderator, Ms. Lawrence. Thank you very much again for the introduction and for helping me out throughout this brief. If you could keep an eye on the chat window for me, and if there's any relevant questions that come up, just let me know. If there are questions, I will try to finish my thought on that particular topic and then take a pause. And I do have breaks throughout the discussion for some specific Q&As that may be related to that specific section. And then there's a large Q&A portion at the end. And with that, I'd like to pause and say, are there any initial questions first for me before I go ahead and get started?
Hey, Brian, we have one question. To what extent does magnetic-based navigation aid your mission?
Okay, yeah, that's a good question. So we do have magnetic-based navigation, but for the most part, when we are working in the missions that we support for NOAA, we typically are referencing true heading and true position. So we have a couple of systems that meld, magnetic uses with, the true headings that we get out of our systems. But I can't think of a situation where we are utilizing magnetic-based navigation to support a specific NOAA mission. Does that answer the question? All right, so as I mentioned, I am an instructor navigator and the Chief of Training for NOAA's aviation-based operations in Lakeland, Florida. We do operate a multitude of aircraft. Here at the Aircraft Operations Center, we have 10 different aircraft. Those aircraft are made up of the lights and the heavies. The light aircraft, which are made up of 4 DHC-6 Twin Otters, 2 King Air 350s, 1 Turbo Commander 1000. These aircraft serve a major component of the missions of NOAA that we do here at the Aircraft Operations Center, including snow survey, coastal mapping, gravity, Arctic heat, and then a multitude of marine mammal surveys. The larger aircraft, the 2 P3s and the 1 G4, those are known as our heavies. These aircraft are the one that we traditionally refer to as hurricane hunters. These heavies also serve as data collection platforms for gravity, atmospheric rivers, some tornado research, satellite data validation, and then ultimately hurricane research and reconnaissance. While quickly being able to go down a rabbit hole about any of the missions that I just discussed, I want to recage back to the specific aircraft and missions that I serve on particularly. So the P3 or the WP3 Delta, we have two of them. They're lovingly referred to as Kermit and Miss Piggy. These are NOAA's aircraft that actually fly into the hurricane. We really love these aircraft. They've been, with NOAA since the 1970s, and they were built specifically for NOAA. But I often get the question, are these aircraft in some way, shape, or form different from the standard P3 that came off of the Lockheed Martin line? And the answer is no, they aren't structurally different. There's nothing added to the structure of the plane that allows us to, in some way, shape, or form, take on more forces. They are a structurally, sound aircraft, and they are kind of a standard P3. Now, on the inside of the aircraft, that's where it gets a little bit different. The inside we refer to as the flying laboratory. And it's chock full of sensors and instrumentation to be able to gather data on some pretty awesome weather events. As you can see here, we're kind of walking up the tube, and we're walking next to scientists, instrumentation. That's the flight director there on the left, and the navigator right there on the right. And so there's tons of sensors on the inside, and our rack configuration is a little bit different in order to be able to plug and play different sensors for different missions that we support. Some of the primary sensors that this aircraft does utilize are radars, and that's kind of one of our bread and butter items that we get, or that we have, excuse me. Our multi-mode radar, which you can see here on this slide, is labeled as the lower fuselage radar. That's an X-band radar that can look really far out and has a really detailed resolution, both for safety of flight and data collection. Because I can tell you that there are weather events out there that even we won't fly into. Our tail Doppler radar, which is the one on the tail, is essentially a radar that's kind of flipped up on its side. And as we fly through the storm or through a weather environment, what we can do with that radar sometimes is get almost like a 3D image of the weather that we're flying in or near. And that it almost acts like an MRI. So we can coagulate all of that data together and build a 3D model. And then that data gets fed into the actual weather models that feed the forecasters that ultimately, feed the nation and our communities their information that they need. The nose radar is a C-band radar that's up in the nose. You see that on the top right. That's primarily reserved for safety of flight and situational awareness, and that is controlled by the pilots in the front. Again, we have a multitude of other sensors, but one of the key sensors that we utilize when we're in the hurricane environment, and then along with some other missions that we serve, is called the SMRF, or it's the Step Frequency Microwave Radiometer, and we typically call it the SMRF. That is a passive sensor that allows us to kind of determine wind speed at the surface of the water body that we're flying over, because ultimately that's what we want to know. That's the data that supports the intensity forecasts for a hurricane, for example. And there are other sensors, and there are other situations. It's not solely fed by the SFMR. It's just a piece of data that they use to kind of build everything together for the picture for the community. There are a slew of other instrumentation depending on the mission that we do. We also carry and launch drop wind sondes. So these are pushed out of the back of the aircraft, and they measure a bunch of different things, being position, wind speed, pressure, temperature, and humidity as they fall. So the P3 will do this as we're flying through the hurricane. And then you can see here in this image, the G4 aircraft, the other hurricane hunter lovingly referred to as Gonzo, that aircraft will fly up above the hurricane and around the hurricane and drop these drop wind sondes as well. And ultimately, we want to collect the environmental data that is feeding the hurricane so that we can better track and better model what the hurricane is going to potentially do in the future. When conducting a mission, we typically fly with a component of somewhere around 11 to 18 people, depending on how many scientists we take. That is made up of 3 pilots, 2 flight engineers, 1 flight director, 1 navigator, 2 in-flight technicians, and typically an assortment of scientists, like I said, again, depending on what mission we are serving. When I'm preparing for a flight as a navigator, you can see me down in the bottom left there. What I'm doing is I have a dedicated Navigator laptop that utilizes programs called Falcon View, combat flight planning software, and then systems with I have another iPad that has a program called ForeFlight on it, and that's just for general aviation kind of updates. I also utilize a program called Winder that pulls wind data off of the internet based on the most recent forecasts, and all of that collaborated together helps me develop basically a plan or an outline for how long it may take us to get to an operational area, and in a sense, how long we're going to have to collect data within that environment. One of the big things that I also do is generate in-flight updates and fuel calculations. Again, it's all to feed how much data can we collect, how much time are we going to have to collect the data, and a lot of that starts with these initial calculations so that we can better base our takeoff times adjusted around some weather phenomenon that the scientists are actually trying to collect the data on. All these calculations have a very significant weight, you know, like I said, on takeoff time. But one thing that Ms. Lawrence is very understanding of is confirming airspace. One of our big partners that we utilize when we're going for these hurricanes is the FAA, and we have a memorandum of understanding with several of the regional FAA facilities that help us, you know, get out to the storm safely and make sure we're properly deconflicted with other aircraft. And ultimately, we want to get out there and we want to orient our pattern in a specific way. So in the northern hemisphere, the hurricanes spin counterclockwise. So you can imagine we like to ensure that we have the wind at our back whenever possible. So understanding the big picture factors that affect our total mission profile time really benefit the scientists for the most efficient use of our time that's available to us. So I did mention that we have an iPad. On that iPad, the pilots also have an iPad, and we utilize a program called ForeFlight, and that's mainly for IFR operations when we're trying to deal with actually giving the FAA flight plans, so they know that where we're coming from and where we're going to. Because a lot of times we're going out to a storm environment and we're maintaining a certain distance from the storm, and we're there for maybe 6 hours, and then when we need to come back, we have to coordinate with the FAA to make sure that we're on the right airways, or that we're going at the right speed or at the right altitude. So we utilize that program very, very much. I also research airspace, like I addressed a little bit, but one of the specific airspaces that we work with so much with the FAA is called a weather reconnaissance area, or a WRA. And what this is a way for us to safely conduct hurricane operations within the storm environment with other aircraft, because we do fly sometimes with the Air Force hurricane hunters, and so we can properly deconflict without the FAA having to have control over us, essentially, and dictate which way we need to go or where we need to go. So essentially, we block off a giant area around that hurricane, and then within that area, we are responsible for our own, you know, safety of flight and deconfliction with other aircraft, and that's in accordance with a pretty robust policy called the NHOP, which is the National Hurricane Operations Plan, and there are procedures within that plan. Once on board the aircraft, the navigational systems that I use are 2 GPS embedded inertial navigation units with 2 GPS antennas. One of those GPS antennas actually goes into a splitter and diverts to both of the inertial navigation units. And then those navigation units can determine a GPS blended solution. And that's typically what we use to drive, you know, the safety of flight systems. That second GPS antenna can be utilized by the sensors in the back, and there's multiple splitters from both GPS antennas that go to an exorbitant multitude of different sensors that utilize position and even true airspeed, things that get pulled off of our inertial navigation unit, excuse me. And then my interface is the CDU 7000. So this is pretty typical within a P3. So when I was in the Navy, the P3s looked like this. We utilized the same inertial navigation units and the same interface, that CDU 7000. During pre-flight, I will ensure the navigational systems are brought up correctly and do some comms checks for our long-range radios. I'm also typically confirming airspace, like I said, with that WRA, but during pre-flight, I'm usually confirming that airspace, making sure that our position and working with the forecasters and our flight director, making sure that the position of the storm is actually where we think it's going to be. And then I have to do some dead reckoning because the storm is moving itself and kind of pick the best solution for where we need to place that WRA so that we can safely do it and safely operate where we want to operate. For the comms I touched on a second ago, I'm responsible for the long-range communications. So we have 2 digital HF radios, we have 2 separate sat phone systems, and then I can communicate on any one of the short-range radios that we have. We have 2 VHF radios and 1 VHF UHF radio. So I want to pause there, and I want to maybe take a second for any questions before I start getting into the missions that I actually engage in and some of the navigational hurdles that we face. So I'm going to pull off my screen here, and I'll just bring it back to my camera for any questions.
So you have 2 questions. First one, how many drop zones per mission and per hurricane?
Yeah, that's a great question, and it's really dependent. So it depends on what mission we're facilitating. I have seen so sometimes when we go into a hurricane, there are multiple scientists from different parts of our organization that are trying to meet their goals. So one scientist from one part of the organization might want to drop one or 2 SONs that are kind of dedicated to them. For example, we often work with a portion of NOAA called the Hurricane Research Division, but then we may get national level hurricane tasking from NHC, the National Hurricane Center. So the National Hurricane Center may ask us to drop a certain amount of SONs, and then HRD, the Hurricane Research Division, may ask us to drop a couple of SONs. So I have been on a mission where we have dropped 1 SON, and then I've also been on hurricane missions where we have dropped on the order of 30 to 40 SONs. Does that answer the question?
It may take a minute for them to come back with that, but I'm going to go to the next question, and then I'm going to let Mark let us know if that answered his question. The next question you have is, are your EGIs keyed?
Okay, I think that's referring to do we load crypto into our navigational system so that we can pull the PPS or the positioning? So the answer is no, we do not key our navigational systems. We don't carry any crypto or anything like that. We did in the Navy. I think that's what you're referring to. Please tell me if I'm wrong. I did that in the Navy when I was working with these same systems, but we do not do that here. No.
All right. I'll wait again for them to respond. It takes a minute. We have a third question. Any issues with receiving a GPS signal?
I've only seen a couple of times where we had a little bit of an issue receiving GPS signal, and that was mainly around the polar regions. I will get into one of the missions that we facilitate that we just recently did out of Alaska, and we were going up over the polar regions. And it wasn't enough for me to be concerned, but it was relatively intermittent. And that's ultimately, that's why the inertial navigation units do what they do. They will run their solutions separately from that GPS embedded signal or that GPS blended signal. And then it's my job to ensure that all of the systems are accurately running. And if they're not, if we were to lose GPS per se, then I would have to switch over the primary, navigational solution to just the inertial. Does that answer that question?
Okay, I'm going to let you know. I'm sorry, I'm going to jump back and forth, but Mark, who asked the question about the drop zone, said you did answer his question. Now I have 2 more questions. And this is from Mike. Wait a minute. One is from Mark. What kind of accuracy do you get with GPS?
Yeah, that's hard to say. I think that we are working on a solution that is within. I'm trying to remember exactly where I see it on the CDU 7000, but we're working within degrees, minutes, and seconds, and then the seconds even go down to first decimal. What I'm looking at as the user. Now that being said, I think that there is some scientific equipment in the back that is trying to monitor GPS at a higher resolution, and I know that for the scientific community, ultimately, higher resolution GPS could help us in certain positions. But I think for the collection in the missions that I have served on, our current resolution is adequate for what we're trying to do.
Okay. Your EGI question about keying, that was what they wanted to know. We have one more question. How long can you sustain accurate flight plans in a loss of a GNSS fix?
I don't quite understand the question. So if I were to, could you repeat the question, ma'am? Sorry.
Yeah. How long can you sustain accurate flight plans in loss of a GNSS fix? What I think this question is saying is, if you lost GPS, how long can you sustain accurate flight plans if you lost GPS?
I've been on missions where we totally lost GPS. This was back in the Navy. We happened to totally lose GPS, and we continued the mission for hours. So a typical mission within NOAA, we typically won't go over 10 hours, where I have been on the occasional time, but I can remember back to my Navy days with the same system, losing GPS, and we were fine. The inertial navigation units have, essentially a self-monitoring system within them that allows a certain amount of drift or not. So I monitor that, and I have very, very rarely seen the inertial navigation units themselves drift out of tolerances. It has occasionally happened, and then in that case, one drifted out of tolerance, but the other one didn't. So I would maneuver the entire, solution or the system driving the solution to that second one. And then I can realign the first inertial navigation unit off of the second one again. But typically that will start to drift out of tolerances again. If it's drifting out of tolerances, it's usually going to continue to do that. And in that case, if we were pretty far from home, that would be a situation that I would kind of bring up to the aircraft commander and say, hey, this is something, we've lost one of our systems. We have a backup system. We're on our redundant system. Maybe we need to consider, heading home and breaking it off at this point. Hopefully that answers the question.
Okay, and that person did say they were talking about GPS, so I think you just did answer that question. One last one. How does your typical flight path look like when you're approaching a hurricane?
That's a great question, and I'm actually going to answer it when I get into the mission. So first, I'm going to talk about tornado research. Then I'm going to talk about one of our missions where we do satellite data validation and calibration. And then I'm going to get into the hurricane mission, and I have a slide that kind of orients you to what one of our flight plans actually looks like. So I will be able to answer that question here in a few minutes.
Okay.
Okay, I'm going to continue. I'm going to share my screen again, and I'm just going to continue with the talk. Okay, so like I mentioned before, I'm going to go in and take you through several of the different missions that we facilitate with our P3. Here at NOAA, one of the first one I'm going to talk about is tornado research. So you can see here on this picture, just up at the top of the image, there's two tornadoes that are starting to form. And this is an image that's taken out of the Navigator window on the P3. So you can kind of get a reference of how close we get to these systems when we're flying on this particular mission. I have flown in support of two different tornado research projects that ultimately kind of were trying to drive the same problem. One was Vortex, known as it's known as Vortex, called the Verification of Origins of Rotation in Tornadoes Experiment Southeast. And that was out of Huntsville, Alabama. And then the other one I did was Taurus, and that one's targeted observation by radars and UAS of a supercell. And I did that one out of Salina, Kansas. At the top of the image here, those two tornadoes you saw, what we're trying to do here is we're trying to get the aircraft in the right environment to observe those kinds of weather phenomenon, essentially. So we were, for this particular picture, we were right at the right spot at the right time, which was a pretty cool situation to be in. What we're doing in this project is we're attempting to fly close to these supercells that come across the United States and observe the environmental conditions that may be conducive to tornado creation. In this image on the left, you'll see a picture that was taken from the ground, and then on the right was one that I took from my window. It's kind of hard to see, but the gist is that we were able to take this image at almost the same time, and you can see what it looks like from the ground and how scary that may potentially be to someone in one of our communities. So we really take this research to heart. We want to capture that data and develop algorithms that support the models. So ultimately, we can accurately assimilate that data and determine the likelihood of a tornado generation. So that comes to you in the community as tornado watches and warnings. So ultimately, those watches and warnings are driven by algorithms that are fed by our science and kind of being there to actively observe the environment that may create tornadoes. So you can see in this particular image right here, we're flying next to a supercell, and then there's this small little hook right at the bottom. And that's really indicative of the creation of what we call a mesocyclone, which may produce a tornado. So when they see these hooks in these supercells, and the whole cell itself is moving pretty rapidly, that would essentially set off an alarm that says, hey, this cell may create a tornado, and then that's when a tornado watch or warning may pop up. So all I can say, the best thing that I can say, and I'll continue to reiterate this throughout my brief, is that please, please, please heed your local warnings. Your local emergency managers are the people who are the most knowledgeable about your local area and the weather phenomenon that may affect you. So please, again, please make sure you are paying attention to your local emergency managers. During this project, I, as a navigator, will help determine total time of the intended mission. So we're taking off out of Salina, Kansas. The scientists are looking at a specific set of supercells that they want to go fly on. Well, how far away is that set of cells? Are there any impediments to us getting there from where we're taking off? And then what I will do is pre-mission coordination with the primary investigator to determine how long it's going to be. So how long it takes us to get there determines how long we have on station, because ultimately, we only have a finite amount of time that we may be able to fly. So the scientists may consider one area over another, depending on the timing that it takes us to get there, that may give him the most efficient use of the aircraft and people. So typically, we will fly, when we flew this out of Kansas, we flew anywhere that was east of Denver all the way to the Mississippi, as far north as South Dakota, and as far south as southern Texas. And the feasibility of position and timing to and from those specific supercells is so ingrained in this mission that it really it's really intensive on the navigator, because a lot of times you're doing these calculations in situ, or you're on your way to a specific region, and it doesn't develop like the scientists wanted. So he is looking at ground-based radars for all of the different targets that we may be able to access. So, and he's constantly feeding me that information as the navigator, and I'm going through calculations over and over again to try and get the position, distance, time just right, so that we can maximize the amount of use of the aircraft. On top of that, we typically conduct this particular mission at 2,500 feet AGL, and what that means, that's just above ground. So we're relatively shallow, relatively low in altitude when we're doing this mission, because we want to be relatively close to the ground, because that's where the tornadoes end up forming. So when we're painting that cell with our TDR, which is that tail Doppler radar on the tail, that's creating that 3D image of that storm. We want to make sure that we're as close as we can get to the actual area that's going to potentially generate a tornado. So my job as the navigator, when we're flying at 2,500 AGL, I'm kind of the big picture view guy. So I've got digital charts, actual charts, VFR sectionals. I've got my iPad up, and I'm constantly monitoring any obstructions that may be around us because we're flying at 2,500 feet. It's very likely that there could be a tower that may go that high or that may affect us in that way. So I'm looking for obstacles. If we're, if we're near Denver, you start to slope up into the Rockies and making sure that the aircraft is safe at that point. To touch on what Ms. Lawrence does again with the FAA, when we fly this mission, we are under IFR conditions, meaning we are constantly communicating with the FAA, the regional FAA controllers, and they help back us up as well when it comes to obstacles and any altitude warnings. So I'm very appreciative of that during this mission because, as you can imagine, it's very dynamic. We are flying really close to a supercell that could potentially be creating a tornado, and it's constantly back and forth communication for us to make sure that we're flying the aircraft in a safe environment or in a safe way. And then throughout the flight, I will analyze ground radars along with the primary investigator and our flight director, who is our in-flight meteorologist. I will analyze those ground radars, and ultimately what I'm looking for is there any storms or is there any lines of these big thunderstorm lines that typically happen across the Midwest that may impede us from getting back to where we were home based. And that has happened a couple of times on this project when I was flying. And in that situation, we had to knock it off early, so in order to not get essentially boxed in, because these supercells, these giant thunderstorms with a lot of vertical convection, are situations that we don't fly into. We won't fly through a supercell. Excuse me. All right, with that, I'm going to move on to our next mission that we support. This mission is one we typically refer to as ocean winds. I have specifically operated and supported this mission out of two different locations. One was in Shannon, Ireland, and two was in Alaska. And this mission ultimately is trying to develop, wind data. And what they want to do is they want to get high winds in the off season of hurricane season. They want to fly through weather phenomenon that have high winds. So one of the locations that happens to be accessible is in the North Atlantic, when weather systems move really quickly across the North Atlantic, hence flying out of Shannon, Ireland. And then another area where it happens is south of Alaska in the winter months. So this depiction right here, what you see is kind of one of our pre-mission briefs that we may get from a scientist. Outlined in red is the operational area that we want to work with. And this is south of the Aleutian chain flying out of Alaska. Excuse me. Overlaid in the green, yellow, and orange is the estimated wind field. So ultimately, if we're looking for high winds, we want to go fly where the orange is. And the gist or the whole deal is that we want to fly in those high winds so that we could potentially calibrate our sensors, and then also potentially calibrate and validate the sensors that are happening with satellites passing overhead. So again, this mission really serves as satellite data validation and calibration. I, as the navigator, oh, I'm sorry, one thing I wanted to mention as well is these dots, these blue and purple dots. Those are buoys that are on the surface of the ocean. So those collect wind data as well. So a lot of times we will try to fly over those buoys and compare the data of the buoy to the aircraft. And if we happen to get a satellite that's passing over at the same time, that would be even better. We would be able to calibrate and validate data that's happening at the buoy, at the aircraft, and up on the satellite. So one of the things that I will do in this mission as the navigator is really help determine if we're going to be utilizing any special use airspace. I will help determine the total time of the intended mission, again, just like that tornado research mission. Depending on how far we want to go or where we want to go will help dictate how long that mission is going to be. Sometimes, for example, when we were flying out of Shannon, Ireland, it was well over 1,000 miles away, and we were south of Iceland, east of Greenland, working a bomb cyclone that had come across the North Atlantic. And our diver airfield was within Iceland, but it had 80 knot crosswind. So we were 1,000 miles away from the closest landable airfield, you know, in a very robust storm moving across the North Atlantic. So I, as the navigator, had to have keen awareness of, you know, how much time it was going to take us to fly home, what our fuel calculations were, what the winds were doing. So I'm constantly doing that, especially when I'm further and further from home. Like I said, the whole goal of this project is collect data and compare that data to that being collected by satellites. And I help determine the feasibility of position and timing to intercept those satellites. What I want to move to my next slide. So this is a secondary mission that we were doing out of Alaska, but it helps me kind of hone in on why it's so important to position, navigation, and timing. What we're measuring, you know, through remote sensing in our onboard sensors is typically wind speed, but in this particular case, we were measuring ice thickness with one of our other sensors. But the satellite is going to be able to measure the ice thickness as well. So you can see here, there's 2 different tracks for 2 different satellites, and we want to be able to maximize our time on that track underneath the swath of the satellite. So as you can imagine, you want to back that up and, you know, into all your calculations when you're trying to fly an airplane 600-700 miles away, and you want to hit this exact spot at the exact same time as a satellite. Now, to compound that a little bit, there was 2 different satellites and they were coming at 2 different times. So what we wanted to do is maximize our time on the swath of both satellites. So that is a very intensive calculation for the navigator to kind of work through those problems, especially in flight, because you're constantly reevaluating and kind of working with the pilots and the flight director to say, hey, are we going to make our window? If not, do we need to speed up, or actually sometimes do we need to slow down? Are we moving too fast and we're actually going to be out ahead of the satellite and miss the window? So this is really cool to me. You know, this is, like I said, this is pretty intensive on the Navigator. I get to engage the scientific community. I get to engage, you know, my crew, and a lot of times I'm really developing the solution for how we're going to go out and attack this plan. And one of the things that I really enjoy about this particular experiment and this particular mission is in facilitating it is that this one is really cool because the sensor configurations that we utilize on the aircraft it's almost like a test bed for the sensor configurations that we're going to put on future satellites, and that's already happened. So you know, the scientists that are responsible for this mission, they have, you know, proven that data collection with antenna in a certain configuration is more beneficial to the data that people are trying to collect off of satellites, and that adjusted the antenna configurations on satellites that are going to be launched into space. So that to me just kind of wrapped up my whole, you know, interest in this mission. Is like we are seeing the effects of our mission, you know, almost not real time, but almost, you know, close to in the future, where you're getting that feedback that what you're doing is really making a difference and making a change. Because ultimately, if we can get better sensors, we can get better data. If we can get better data, we can feed better models. If we can feed better models, then we can increase the amount of time that we can notify communities about some impending weather event that may affect them, you know, adversely. So ultimately, we want to get that data in the hands of the communities as early as possible. All right, I'm going to shift gears now to the hurricane work that we do. And then again, I will open it up for Q&A at the end of the mission set here. This slide is a quick representation of how hurricanes form, but the gist is that they start off as a broad area of thunderstorms, thunderstorm activity, and then they start to kind of pull and coagulate together as that whole weather system moves, and it's helped by heating and cooling of the ocean. That's why you always hear about the temperature of the ocean and the temperature of the environment can feed these hurricanes. And then it's helped out a little bit by the curvature of the earth, by the spinning of the earth, which is why in the northern hemisphere, hurricanes will spin counterclockwise. In the southern hemisphere, they'll spin clockwise. So we operate out of Lakeland, Florida, and this is to answer the question that was asked earlier. This is what we call a butterfly pattern, and this is pretty typical of one of the missions that we support when we're going out to fly a hurricane. Like I said, we operate out of Lakeland, Florida, but in the past, we have operated out of a multitude of forward operating bases. So the Atlantic hurricanes that affect the most amount of US citizens end up generating typically in the East Atlantic off of Africa. So we will forward deploy down to places like Barbados, St. Croix. We've even done Bermuda. We'll fly out of Lakeland, and then a multitude of air bases up along the East Coast, depending on how far we actually want to track these hurricanes. And then when we facilitate the Hurricane Research Division, a lot of times we are trying to research the genesis of a storm. So in that particular case, we went down to Costa Rica to fly out of Costa Rica on Pacific storms because they generated just off of the coast of Costa Rica, just off of the west side, and kind of moved up towards Mexico. Because that's a lot easier for us to base out of than somewhere in Africa. There has been communications about trying to do that, trying to get in a position where we're monitoring or where we're looking at the genesis of hurricanes that happen in the Atlantic. I just haven't been a part of those missions yet. So during this project, during the hurricane mission, what I as the navigator will do is, again, I will coordinate the special use airspace. So I will do this on the pre-brief. I'll do it up into my pre-flight, and then a lot of times I'm even coordinating in flight with the FAA to make sure that we have an area blocked off. For example, when we're talking to Houston Center and there's a hurricane that's coming up, or a tropical storm or cyclone that's coming up in the Gulf of Mexico, a lot of times the weather north of that system is still good for flying, but we want to have basically a 200-mile circle around the hurricane. So we will work with the FAA to maybe truncate that circle on the northern side so that aircraft can fly back and forth on the coast and get things done before the impending event. So it's really a dance. It's back and forth with the FAA in flight when we're doing this a lot of times. If the storm is way out in the Atlantic and it's where no one's really going to be flying, it's usually very plug and play. We just plop in a position and we put a 200-mile circle around it, and then we will update that position with the movement of the storm throughout the mission or throughout the series, because multiple crews may be flying on the same hurricane within a couple of days of each other or something like that. So once in the storm environment, I'm constantly calculating the position, direction, and velocity of the storm. So what we want to do is in order to facilitate the best data collection for the scientists, is a lot of times we want really straight, smooth tracks through the hurricane. So as you can imagine, the hurricane is moving. So we want to almost intercept the center of the hurricane as it's moving. So I'm primarily responsible for those calculations. How fast do we need to go? How fast is the storm? And then essentially calculating an intercept point. And then as we cross the eye wall, we want to make sure that we cross that eye wall at basically a perfectly perpendicular angle. You don't really want to catch an eye wall tangentially, because that's where the roughest part of the storm is and where you get the most vertical convection and the most bumps essentially that we see. So we want to hit it perfectly perpendicular so that we spend the least amount of time in the eye wall. And then we're going to work, our flight director, in-flight meteorologist, is going to work to find what we call the zero wind center. So he's got sensors and a system that helps him drive the aircraft towards the actual zero wind center. And then the second that we mark that center, my job starts again. I mark that center, I evaluate how far the storm has gone based on previous data, and then I kind of extrapolate where I think it's going to be. So ultimately, by the time, for this example, if you're looking in the top right picture, if we hit point 2, we come through the center of the storm, we're on our way to point 3, I need to calculate a good point 4 so that I can get a straight line perfectly down the azimuth that the scientists want towards point 5 that intercepts the center of that moving storm. So that's what I'm doing. I'm trying to get the exact center. I want to get it perfect every single time, or at least that's what I'm striving to do. But You can imagine, just like tornadoes, hurricanes do sometimes have a little bit of a wobble, where that center will kind of wobble around. So it's not an exact science when I'm just utilizing extrapolated DR positions to find the center where I think the storm is going to be. And that's where the crew collaboration comes into. When we're maneuvering towards the center of the storm, for example, we're going from point 4 towards the center down to point 5, the flight director, the in-flight meteorologist, will start to look long range at his radar, and he can see the weather around the eye, and he can, you know, interpret or extrapolate a track that we need to adjust to. And that happens. We may need to adjust 1 or 2 degrees to the left or to the right based on what he's seeing. And a lot of times we have to hedge that towards the movement of the storm. So I will work with the flight director. He'll say, hey, I think we need to go to this angle. And I'm like, oh, by the way, the storm is moving left to right. So we need to adjust that a degree or 2 to the right to apply, account for the movement of the storm. And that applies directly to individual features within the storm. Like I mentioned when we were doing tornado research, that hook, that could generate a tornado, that can happen within a hurricane as well. We can have smaller mesocyclones that formulate within a hurricane. So if the flight director sees something like that, sees a feature within the hurricane that he's not comfortable flying through, he will adjust. He will not fly through that. And then we have to work, again, the whole storm is moving, and then within the storm, those small features are also moving around the center of the storm. So there's a lot of, it's a very dynamic environment. So there's a lot, it's very crew intensive, it's very communications intensive, within the crew as we're, maneuvering towards the center of that storm. So I can't, talk enough about how much I appreciate, my fellow crew members on these missions and how we work together. It's really awe-inspiring, and I'm really happy to be a part of this. So I also, like I said, I will back up that flight director, and this is a small video for Hurricane Dorian, which was a Cat 5 hurricane. So as it's going to seem really slow, but you'll see we get an update on that radar about every 6 seconds. So we're maneuvering towards the center of Hurricane Dorian. We're just about to hit the eye wall right here, and as you can see, a lot of those weather features are starting to disappear, and that's because of the attenuation of the radar beam. So that X-band radar attenuates a little bit more when we're in such an intense weather environment like the eye wall, like right here. And then you'll see as we get into the eye here, you'll see the eye start to kind of appear as that attenuation starts to go away and we hit clear air. So we're working towards the center here on Hurricane Dorian, and we're keeping an eye out for any mesocyclones. If you look right on the north side of the storm here, there's kind of a hook just off the left side of the aircraft. That's something that we would potentially avoid because that could be a potential mesocyclone or notch. And then as we get closer to the eye, the wind speed starts to really pick up. So you can see the crab angle of the aircraft based on its track. That line coming out from the front of the aircraft, that blue line is its track. And the angle of the actual aircraft icon is canted to the left because he's having to adjust for that wind and crab into the wind in order to keep a straight track towards the center of the eye. So as we get closer to the eye, that wind picks up and that crab angle needs to increase. And then once we get into the eye, that wind lessens and they need to, creep that crab angle back over to right off the nose to more match heading. And if you look here in a few seconds, I think it just stopped there actually. If it was to keep going, it would, continue to even out with the nose of the aircraft. Once we get into the eye, like I said before, the flight director is going to hone in on that zero wind center, and then we're going to mark that position, and then my job starts all over again. I did want to mention, so I personally have been through about 100 passes in hurricanes. Last year again was a record-setting season for us, and the people who are predicting this season for 2021, they are predicting an above average season again. So It's not uncommon for in a single season for a crew to pass through the center of a hurricane around 30 to 50 times. Last year it was almost 50 times for myself. Our current record holder for passes through a hurricane is a gentleman who is retired now. He had just over 700 passes, and he is the kind of all-time pass leader. And then we have another flight director who is still active with us at the hurricane operation, or excuse me, at the Aircraft Operations Center, who has just about 640 passes. So at my level of just over 100 passes, I'm still just barely scraping the surface on, observing these hurricanes and in their entirety. So we really lean on those individuals who have past experience, who have been in the environment, who have seen all of the different nuances that may come about. And I'm really appreciative of those seasoned veterans and how they've taken me under their wing and, taken the time to really explain things that happen. So again, I can't preach about that enough, and how much work they do and have done to get me where I am, knowing this environment and talking to you. But I'm still humble, I'm still learning, and I'm looking forward to, more of these missions in the future. So I'm going to pause there for just a second, and I'll come back to, I'll pull off my screen so that we could ask any questions about the missions.
Hey, Brian, we have about 5 questions, and we're going to take these kind of quickly because time is running out. These were great questions. So the first question is, do you have a backup if you can't make the mission?
Yes, typically, well, sort of. So we have 2 different aircraft, and we typically run on like a port and starboard schedule. So if something is wrong with our primary aircraft and the secondary aircraft is available, we may shift over to that aircraft. Now, that being said, a lot of times the missions that we are facilitating within research, which is in researching the mission, can adjust a little bit depending on the model run time windows that we're trying to get to. So what I will say is that our aircraft are pristinely taken care of. I can't support our maintenance and our I can't praise them enough, because it is very rare that we do not make a mission, and that speaks volumes to the amount of time and effort that our whole team at the Aircraft Operations Center spends to make sure that these aircraft are good to go and ready to fly for that mission. On another note, the Air Force Hurricane Hunters, they fly C-130s, and they have a component. They have more aircraft than we do. We only have 2. I think they have on the order of 10 aircraft, but don't quote me on that. So they oftentimes are the ones who facilitate the reconnaissance of the storm, which is actually marking that center for the National Hurricane Center and updating its track. So a lot of times we're working in tandem with the Air Force, and we're all trying to accomplish that, that mission, getting the data in the hands of the forecasters as early as possible so that we can get data and information to communities as early as possible so that they can, properly prepare themselves. Hopefully that answers your question.
Great. Next question. Is machine learning being applied to your data sets to aid in identifying higher probabilities of tornado touchdowns?
I very quickly get out of my scope when it comes to this question. So I'm going to say, I think so. I'm pretty sure that it is, but that is less of a known for me and more of a known for the specific scientists that are developing these, that are working on these projects. So I think the answer is yes, because I can think of multiple times where I have overheard people talking about integrating machine learning exactly for that situation. Is like, for example, take tornadoes. If we can identify when the environment would facilitate a tornado and then a tornado happened, versus an environment that we thought would facilitate a tornado and a tornado didn't happen, we can apply machine learning there and better and get those algorithms better. So I absolutely think that that is happening, but I very quickly get out of my scope, and I'm scared of putting my foot in my mouth if that in that case.
There was something put in the chat for more information on that. The next question: how rough is the transition through the eye wall?
Yep, it's pretty rough. I would say so. What people often ask me is how rough is the ride, and I will explain it that the aircraft doesn't know the difference, in the way it feels. It doesn't really know the difference between a 100-knot wind and a 10-knot wind, as long as that wind is horizontal. You're just moving slower across the ground, but your true, as you proceed through that air mass, as you're moving through that air mass, it doesn't know the difference between a 100-knot wind and a 10-knot wind. But when you get into vertical convection, where the air mass is moving vertically, that's when you start to get into bumps that happen up and down. And that is more common. And within hurricanes, that does happen. In very well-established hurricanes, you get a lot more horizontal motion of the air mass. But you still do have vertical convection. You have movement of air in the vertical spectrum. But as you come through that eye, that's where the most amount of kind of churn happens. So it can be pretty bumpy. I would say that for myself, I'm a little more desensitized to bumps in an aircraft than the typical person flying on an airliner to and from their vacation. So my idea of bumpy may be different than someone else's idea of bumpy. But I can say that if I was, a person just flying on my vacation, what we do can be pretty bumpy. We do have limitations. We have G limits that, on our aircraft that would, if that were to happen, we would knock off the mission and then head home. So we do have policies in place that kind of keep us, from, we have limits essentially is what I'm trying to say. Hopefully that answers your question.
That's a great answer. Next question: how many missions do you fly in a typical hurricane storm?
Yeah, that's a great question. A lot of time it has to do with where the storm generates. So if the storm generates off the coast of Africa and we send a crew out to Barbados, that crew may stay with that individual hurricane through Barbados, St. Croix, Lakeland, and follow it all the way up the East Coast. So we could have, somewhere on the order of 20 missions following this storm for 2 whole weeks, depending on how fast it's moving. But in certain cases where, like in the early hurricane season, sometimes hurricanes will generate in the Gulf of Mexico, spin up really quickly, and then head straight north towards the Gulf Coast. And that oftentimes you may only get the opportunity to fly maybe once or twice on that hurricane before it hits land. And to go down that rabbit hole just a little bit, we often do not fly hurricanes that are encroaching over land. We have a policy in place for, the ability to do so, but there are a lot more stringent measures that we need to follow if that is the case, because as that hurricane starts to interact with land, there's a lot more friction. That friction can create more, vortices and essentially tornadoes, and it gets a little bit more dangerous. So we tend to not fly hurricanes that are over land, but we have in some cases done so.
Thank you. Okay, next question. Is there any improvements that can be made to your GNSS/GPS receiver to aid in your flight calculations?
I'll have to take that one for action, really. I don't think so. Just off the top of my head, I think that the system that we have is able to facilitate the positional accuracy that I need to be able to determine those calculations to and from the storm and where I think it's going to be. Now, that being said, I know that the scientific community is always looking for higher resolution when it comes to positional data, especially 3-dimensional positional data for us within the storm. So the more accurate that we can make that positional data, the more accurately we can find out where a specific feature was that was in the storm and where that feature moved to. And that can support modeling, and I know that for a fact. So for me personally as a navigator, I don't think so much for the weather scientific community at large. I think there's definitely room for growth.
Okay, great answer. Next question. How do you pick the altitude when passing through a hurricane?
Yeah, that's a good question too. A lot of times that is driven by policy and also driven by what's happening within the weather. So one of the particular things that we pay attention to is the freezing layer. So where is this hurricane within the latitude of the Earth? So if we're further north, the freezing layer may be lower. So we want to pay attention to, because we're flying through precipitation, through clouds, we want to make sure that we're staying away from icing conditions that happen on the aircraft. So the Hurricane Center typically wants their fixes of the center of the hurricane at 10,000 feet, and they want that at 10,000 feet pressure altitude. And I say pressure altitude because we're moving into a very low pressure system. The hurricane is a giant low pressure system. So your actual altitude over the ground actually maneuvers up and down with the changing pressure. So we will keep a constant pressure line that we want to fly on, but our actual vertical height off of the ground is actually changing, and that's accounted for when they make those fixes. So we typically fly at 10,000 feet. When the Air Force and us are flying at the same time, we have to be separated by 2,000 feet within the storm. So we will fly at 8 or 12,000 feet. In certain cases, when we're doing an invest on a mission or on a cyclone that is just starting to come together, when it's a very weak storm, we will fly lower. And I've been as low as 1,500 feet. In a very broadly unorganized tropical depression that really just appeared on the radar as a bunch of different thunderstorms that were just kind of swirling around each other. So hopefully that answers your question.
Okay, last question. You mentioned you compare real-time data with buoys,
Yeah.
rather. Do you also compare data from vessels, maybe via the VOS program?
I can't think of I know that we could, and I'm thinking of a project that I was not part of called Atomic, that they were flying out of Barbados. And that particular mission, they were trying to analyze the environment, but they also had ships. They had ships that went out and were analyzing the environment as we were flying over. And I think there was also some UAS operations going on. So I wasn't a part of that mission. The missions that I have been a part of, I can't think of any situation where we were utilizing data from ships, but it's perfectly feasible for us to be able to do that. A lot of times we are, these missions are so dynamic that if we were to try and work with a entity that is a little bit slower, a ship, you're typically moving at 10 knots or so, and we are moving at hundreds of knots. And any delay in time that we may face, even a 30-minute delay, you could be off by, 30, 40, 50 miles. So I could see it logistically being a little bit tougher to coordinate with a vessel or something like that. But that being said, it's not impossible. And if that data were there and we happen to be in the same environment and it was shared, like we would absolutely use that data. Okay. Hopefully that answers your question.
We're good.
Okay, that's the last questions. Let me just double check my notes here. Yeah, I've got one more slide, actually a couple more slides, but I've got one more slide that I want to present to you. So I will share my screen. So lastly, I want to end on this slide. On this slide, you'll see the difference in what storm model runs with data provided by us and without data provided by us. So to me, this is a excellent example of why I think what we do is important for people, communities, and the country as a whole. The whole goal here is to collect the data in a timely manner so that we can ingest it into the models and increase the prediction capabilities of forecasters. If we can increase that lead time, we can better determine where the storm is going to go, how strong it's going to be, then that gives opportunity to communities to better prepare and even potentially evacuate. So I can't say this enough to, like I reiterated it before, please pay attention to your local emergency managers, heed their warnings. And because a lot of times we are trying to develop relationships with the community at large. So hopefully this slide presents that to you and kind of an understanding of why we do what we do. And ultimately, I truly believe, me personally, I truly believe that the work that we do saves lives. I'm so happy to be a part of the organization, an organization that believes in that too. And this slide perfectly kind of depicts that. If we weren't able to do what we do, we would not have been able to accurately depict where this hurricane was going to go. And ultimately, more communities and more people could have suffered for it. So we are constantly learning. We are constantly trying to make our solutions better. And ultimately, the goal, my goal in what I do every single day is to save more lives. And I truly believe that I'm doing that. I truly believe that we are doing that. And lastly, I just want to say thank you to the Institute of Navigation for having me. I'm honored to be here. I'm definitely planning on becoming a member. And with that, I want to open it up for questions. So I'll pull it off my screen and then I'll just bring it back to myself for any last questions.
I don't think we have any more questions, but Brian, we'd like to thank you from the Institute of Navigation. That was a fantastic briefing. The data was very informational. It gives us what we need to understand. We need to respect what our meteorologists are saying. And we know that you and your team is a strong contributor to the safety of what's happening when we are dealing with hurricanes and tornadoes. So we want to thank you very much for the work that you do and the work that your team does. We appreciate NOAA, we appreciate you. We want to end on, if you aren't a member of ION, please join at ion.org, and reminding you that this will be recorded and you can catch it on the ION website and on the ION YouTube. We want to thank everyone. The questions were fantastic. The briefing was just great. I love the information. PNT until I die is all I can say. Basically, everyone have a great holiday weekend, and we look forward to working more with you, Lieutenant Commander Richards. Thanks, everyone. Appreciate you.